Hello everyone, welcome back to my channel. So in this video we are going to learn about some of the problems regarding basics of electronic devices, that is basics of semiconductor topic, okay, in EDC subject. If you are first time to my channel, please consider subscribing and encourage me to do more videos like this. So in this particular question, in the first question we will take so he has asked to find you intrinsic conductivity and intrinsic resistivity of germanium at 300 degrees Kelvin, and giving that intrinsic concentration Ni is this, and mobility of electron and mobility of hole. Okay, so I have given you the formula for this. Okay, so in the intrinsic semiconductor I have made a video, so I'm giving you the playlist link in the description, so you can from the playlist link you can see the concept of intrinsic semiconductor. There in the concept of intrinsic semiconductor I have discussed about conductivity. Okay, right. So what is the formula for conductivity is, so generally conductivity is given by NQ mu n plus PQ mu p. Okay, so this is conductivity of electrons and this is conductivity of holes. Okay, so in a semiconductor, in an extrinsic semiconductor, so in a general semiconductor, so here what we will take is, in a normal semiconductor, okay, so intrinsic semiconductor, what will take, so for if you generalize this formula, so for intrinsic semiconductor N is equal to P is equal to Ni. Okay, so this we have seen in mass action law as well. So number of electrons, number of free electrons, number of holes is equal to intrinsic concentration. Okay, so Ni Q mu n plus Ni Q mu p. So if you take NiQ as common, you will have mu n plus mu p. So this is the formula for conductivity for an intrinsic semiconductor. Okay, so this already I have told you, but I am again revising this. Okay, so he has given that Ni is equal to 2.5 into 10 to the power of 13 into Q is charge of electron, which is 1.6 into 10 to the power of minus 19 into 3800 is the mu n value, and mu p value is 1800. Okay, so if you do this you will get around 0.0224 mole per centimeter. Okay, you can just check from the calci, just solve it using your calci, you will get around 0.0224 mole per centimeter. Okay, so what is this? Is intrinsic conductivity, and he has asked you to find intrinsic resistivity as well. So intrinsic resistivity is 1 by inverse of intrinsic conductivity, that's all. So 1 by 0.224 mole whole inverse. So what you'll get, so you'll get around 1 by 0.224 is 44.6, right? Mole per centimeter whole inverse, it will become ohm centimeter. Okay, ohm centimeter, right? So these are the units of resistivity, and this is the unit for conductivity. Okay, so units are also important. Okay, so next we'll see one more problem on the same concept, that is basics of semiconductor and doping concept only. So in this problem he has given a pure germanium semiconductor is doped with 1:10 to the, with impurity ratio of 1:10 to the power of 7. Okay, so 1:10 to the power of 7, and he has asked to calculate donor concentration. So that means he has doped with a donor impurity. If we are asking for donor concentration, so he is doped with donor impurity, and then he is asking for electron and hole concentration, conductivity and resistivity of doped semiconductor. That means after doping, what is the conductivity and resistivity? And he is asking to find the conductivity, number of times the conductivity has increased due to doping. So we know that after the process of doping, the conductivity automatically increases. So how many times the conductivity is increasing, you have to find. That is the fourth question here. Okay, right. So how to solve this? So he has given some data to solve this. He has given total number of atoms, that is intrinsic concentration is given. Okay, and then intrinsic concentration he has given, and total number of atoms he has given. Okay, and then your mobility of hole and mobility of electron. Okay, so mobility of electron and mobility of hole. Right, and first of all, first question, so donor concentration. So when you are doped with the donor impurity, donor concentration is the majority carrier concentration. So ND is given by total atoms per cubic centimeter multiplied by impurity ratio. So this is the formula to find the majority carrier concentration if impurity ratio is given for you. Okay, so that means for every 10 to the power of 7 intrinsic atoms, one impurity atom is being added. Okay, so how many total concentration of doping atoms will be there is total atoms multiplied by this ratio, multiplied by this impurity ratio. So you just remember it as a formula. Okay, so ND, that is majority carrier concentration, is equal to total atoms per cubic centimeter multiplied by impurity ratio. Suppose if the semiconductor is doped by acceptor impurity, then also acceptor impurity is equal to total atoms per cubic centimeter multiplied by impurity ratio. Okay, so for both the type of semiconductor, extrinsic semiconductors, the formula is same. So what will get? Donor concentration is equal to total atoms is given as 4.421 into 10 to the power of 22 multiplied by 1 by 10 to the power of 7. So impurity ratio is 1 by 10 to the power of 7. So it will be 4.421 into 10 to the power of 15 atoms per cubic centimeter. Okay, so this is your first question. Next, second question, he has asked to find the electron and hole concentration. So electron concentration, so in N type, when you is doped with the donor impurity, so N is almost equal to ND. We know that the majority carrier concentration is equal to almost doping concentration. Okay, so and this already we have discussed in mass action law also. N is almost equal to ND. Okay, so you can see the concept in mass action law video which I have made in my channel. Okay, so N is equal to ND, so which is equal to 4.421 into 10 to the power of 15 atoms per cubic centimeter. Similarly, hole concentration from mass action law, again from mass action law concept, it is Ni square by ND. So this is from mass action law. Okay, you can see the video from the playlist which I have given in the description. Okay, right, so Ni square by ND. Ni square is, what is Ni given? 2.5 into 10 to the power of 13 whole square. 2.5 into 10 to the power of 13 whole square divided by ND is 4.421 into 10 to the power of 15. So if you solve that, you'll get it around 1.41 into 10 to the power of 11 per cubic centimeter. Okay, so this is what you'll get. Okay, this is what you'll get. Okay, sorry, not atoms, per cubic centimeter only. Okay, so this is how we can find electron and hole concentration. So electron concentration is almost equal to the doping concentration, that is majority carrier concentration is always equal to the doping concentration, and minority carrier concentration is, that is hole concentration, is found from mass action law concept. Okay, so donor concentration we have found, and electron and hole concentration is also completed. Now see the third problem. Conductivity and resistivity of doped semiconductor. He is not asking for intrinsic semiconductor but for doped semiconductor. So when a semiconductor is doped with donor impurity type, then its conductivity, its corresponding conductivity after doping is equal to NQ mu N. Okay, because the conductivity is mainly due to majority carriers. Conductivity in an extrinsic semiconductor is mainly due to majority carriers only. Because majority carriers are more in number, they will give you more conductivity. Okay, simple in concept. So this is the conductivity formula. So NQ mu N. And what is N again? Concentration of electrons. Concentration of electrons is equal to ND. So ND Q mu N. NdQ into mu N. So what is the ND you have got? 4.421 into 10 to the power of 15, right? Into 1.6 into 10 to the power of 19, which is charge of electron, into mu N is given as 3800. 3800, and if you solve, you'll get 2.68 mole per centimeter. Okay, and if you want to calculate the resistivity, rho n is equal to 1 by sigma n. So this is 1 by 2.68. So if you solve, you will get 0.373 ohm centimeter. Okay, so this is how we can find the conductivity. So conductivity, always remember, conductivity is due to only majority carrier concentration in extrinsic semiconductor. If it is donor type, then it is due to electrons. If it is if the impurity is donor type, then it is due to electrons. If the impurity is of acceptor type, then it is due to holes, that is p-type semiconductor. Okay, right. So the fourth question here is, how many times the conductivity is increased in semiconductor due to doping? So this is what very important. So all these, the remaining topics are just formulas, you can just substitute that. Okay, so this is what the concept here is. So in order to find how many times the doping has been increased due to conductivity, what you have to do, so you have to find the conductivity before doping. Okay, so conductivity after doping. Okay, so conductivity after doping by conductivity before doping. Okay, this gives the total number of times the conductivity got increased. Okay, this is the simple formula you have to do. So what is conductivity after doping? This is the conductivity after doping. So that is what we have already found, and it is equal to 2.68. So because after doping, the semiconductor is becoming n-type semiconductor, and in n-type semiconductor the conductivity is due to electrons, so which is given by sigma n. So we have got from the third problem, that is in the above problem, so we have got it as 2.68. Right, so we have to find conductivity before doping. So before doping, any extrinsic semiconductor is an intrinsic semiconductor. Very simple. So before doping, because after the process of doping only, the semiconductor will become extrinsic semiconductor. So the conductivity before doping is intrinsic conductivity. So intrinsic conductivity we have seen in the previous problem. The formula is NiQ into mu n plus mu p. Okay, so what is Ni given? 2.5 into 10 to the power of 13 into 1.6 into 10 to the power of minus 19 into mu n. Mu n is 3800 plus 1800. So if you solve, you'll get around 0.0224 mole per centimeter. Okay, so now we have got intrinsic conductivity and we have found the conductivity after doping. So number of times conductivity increased, number of times conductivity increased is given by, so conductivity after doping is 2.68 divided by conductivity before doping is 0.224. so if you calculate, it is 119.6. so if you approximate, it will be around 120 times. So conductivity is increased by 120 times. Okay, so conductivity is increased by 120 times before and after doping. Okay, so this is how we can prove that conductivity of extrinsic semiconductor is very much high when compared to conductivity of intrinsic semiconductor. Okay, so this is how we can solve any problem if impurity ratio is given, and this is the formula for finding the majority carrier concentration if impurity ratio is given. Okay, normal concept only, but remember it, take it as a formula also. And again, you have to keep in mind the mass action law. So mass action law main purpose is to find the minority carrier concentration, like this. Okay, and then conductivity in an extrinsic semiconductor is due to majority carriers only, because majority carriers are more in number, so conductivity is due to majority carriers. Okay, keep this in mind for this problem. And total number of times the conductivity got increased is given by the conductivity after doping by conductivity before doping. So it is now increased by 120 times. Okay.